Okay, welcome to ELEC, ELEC 3067 26 summer electrical machines course, Fanshawe College, May 5th, 2026. This is week 3 right now. Times go fast. Time goes fast. All right, so let's start. We got a little bit of a mishap with the PC, so let's just start right now. Okay, cool. This is the third presentation from the 3. The other 2 we had during the in-person class, and this is the third one online. So we keep going with the direct current motors, DC motors. Okay. Still, I need to give you a separate lesson on the back EMF. I still owe you. I remember I still owe you one lesson on online, so I didn't forget that. So that's what I'm going to do here. Then, not now. All right. So working power for the for the electrical machines DC motor. The motor converts the power from electrical to mechanical. And the mechanical power, will be the output voltage, and which is the armature voltage right there, times the current. So there'll be the electrical power. The mechanical power here would be the P in watts, and we could have also, it's going to be equivalent to the voltage on the armature, which is the output voltage, and times the current that goes through it. All right. Then also we have that famous formula, which is the speed times torque over 9.55. We went over that last time we saw each other online. And from that we can derive that the torque is, from that formula, torque is 9.55 times power divided by the speed, which is kind of equivalent, not kind of, it is equivalent to K times phi times I. The K is a specific motor constant, which is determined by the physical motor construction, and we're also going to go over that. And the phi is the magnetic flux per pole. How many poles do we see here? There's 1, 2, 3, and 4. And I just noticed, because I grabbed that thing from this side here. Should be north, south, north, south, not north, north, and south, south. Okay. All right. Because all the windings, they have north and south pole. So there should be one set of winding with the, let me just get the pen here. Here's north, south, and there would be north and south, or north and south here. Okay. All right, so this would be a specific winding. Now over here there are only 2 poles. You see that on the top in the field? Only 2 poles. There's 4 poles. All right, so poles in a DC motor refer to magnetic poles, north and south, that create magnetic fields necessary for rotation. Every motor must have an even number of poles. Naturally, it's going to be even number of poles, typically ranging from 2, right here, to 12 or more. The pole counts directly determines the motor's speed and torque characteristics, so it's tied to speed and the torque. So that is what we have here. Now, okay, in this case, the phi, the Greek letter phi, F-I, sometimes people read it as phi, depending where you are in the world. Magnetic flux per pole, and it's in Webers, and Webers, sometimes we call it Webers, is volts times second, volts per second. That probably doesn't tell you much, but it will later. And then, of course, the I stands for armature current. But the mechanical power here, well, we're going to come back to this formula in the next couple of slides. This formula right here, this for the power, it's easier to see if you just write it like this. Power equals speed, which is the N letter, times torque divided by 9.55. This formula, here, this formula right here, I need you to learn in such a way that it's going to become part of your DNA. All right. So we got over the first slide here. Speed control. Let's talk about the speed control here. Here we have the formula speed of rotation, of course, the speed of rotation. And over here we have the separately excited, separately excited motor, which means the armature and the field are excited or fed separately. Or you could also have it in series, which the field and the armature will be connected in series and fed from one power. Of course, with the field, you will have the rheostat going. In the series configuration, you run into something like, you're more likely to run into something that's called a runaway hazard or runaway condition. And when that happens, the speed of the motor goes pretty much into cosmos type of a speed, warp speed. And we could have some spectacular and dangerous failure. So, here we got another formula. Output voltage, or the voltage, the armature voltage here. Divided by the design constant, and that also sometimes is listed as K, and it's determined by the physical construction of the motor. You'll be given that times the magnetic flux per pole. So that depends how many poles you have, but per pole. Right? So that's going to be the speed. How to control the speed? You can control the magnetic flux per pole, or you can control the voltage applied to the armature. Now the relationships between that. Adjust the magnetic flux can affect the speed. So when you have the field resistance goes up, then the current in the field, which probably could be X here, goes down. While resistance goes up, current goes down. Then the magnetic field per pole goes down. That increases the speed. And here is the vice versa relationship between those quantities. Well, what happens if the magnetic field, because when we have the high speed, then the supplied voltage reaches maximum. When that happens, the magnetic field per pole is going to go down, which means it's going to increase the speed. So when the magnetic field per pole becomes close to zero, then the speed is going to go close to infinity. And that would be a dangerous situation. Usually it would happen when you have the field and the armature connected in series. Usually. But there's always a but. Okay? Speed of rotation. Alright. Here's speed of rotation, and there's speed of rotation. We have 2 slides on that. Not sure why is it that we're not getting the transition proper. Okay, no, never mind. Speed. Here's the speed equals. We already established that. And we have the excellent feature. That excellent feature. We can make the magnetic field constant. If we make the magnetic field constant, then the speed control is left up to the voltage control. When we increase the voltage supplied to the armature, because we put that in constant, the field, magnetic field, make it constant, then the speed is going to be determined by how much voltage we're going to supply into the armature. More voltage to the armature, more speed. Less voltage to the armature, less speed. So those are directly proportional. How to adjust this supply voltage? That supplied voltage here. In DC motor, we can use something as the PWM concept. Have you, and I'm going to ask you to respond, have you done the PWM concept, or do I have to explain that? Can somebody respond?
Yes, we play with the pulse modulator in turn 1.
Okay, cool. So I don't need to explain the idea of PWM. All right, right? Thank you for answering. Okay, so we can with the, you probably had this thing with the practical electronics. I just wondered if oh yeah, practical electronics. There you go. I can see that in the chat line. There you go. Yeah, so I remember I taught that course also some time ago, so I know exactly what you've done in that course. So you get the idea of what PWM is, and you actually did some labs that involved small motors with the PWM concept. So yeah, we could install something that's called PWM converter, and we could control the speed by controlling. Does it say duty cycle somewhere? Yeah, there's a duty cycle. All right. So that's one of the concepts here. Where are we? Power flow. Did I miss any slides here? No, I didn't miss that one. I didn't miss that one. Yeah, we got that. So let's go to the power flow here. Now, separately excited motor. It is also the lab that we're going to use. There's the shunt configuration or series configuration in our lab equipment. Shunt is that the field is excited separately, being fed power or voltage into it, and the armature, as opposed to, as I said before, series configuration when the armature and the field are connected in series. And of course we adjust the rheostat to the field that we could well, control it somewhat. But when we have the things in series, then yeah, it gets a little bit more, but you do get a lot of power out of that one. Right. Now, input power in this separately excited motor, which is the shunt configuration, the input power is going to be equal, or it is equal, the power that is going to be supplied to the armature and the power that is going to be supplied to the field. Electrically, that's what you're supplying. So that will be the input power that you have to give it to the motor. So, of course, the armature power is equal to supplied power times current. And the magnetizing power is going to be equal, or it is equal to field. See that X thing here? It's field. Power in the field equals to voltage, field voltage times the current. Well, voltage and current. Of course, just by the look at the formula, you can probably tell that we're dealing here. We are dealing with the RMS type of quantities here, current and voltage. And okay, mechanical power is the output, because this is a motor, so we are supplying the electrical power and we're getting out of it mechanical power out of that machine. So the mechanical power, remember that formula that I am asking you to learn so you have it part of your DNA? Torque times speed divided by 9.55. And torque is in Newton meters in this case, and the speed is in rotations per minute, RPMs. Alright, so what do we have? The losses. Where do we get the losses? Well, the power, we always have to put in more power to get, and we're going to always get less power out of whatever the machine that we are putting the power in. That is always excuse me, that is always the case. If it were the other way, then we would be gaining power out of thin air, and that's just not happening. So the difference of the whatever we have to put in, subtract by whatever we're actually getting on the output, So the difference between those two equals to the losses. Now, when we want to calculate the efficiency, okay, again here, armature power plus the field power is the input power, and those are electric power. And out of that motor, separately excited motor, we get the mechanical power, the output power, which we have the formula here. And those are going to be different. If you have the sum of these two powers, it's going to be way more than what's coming out because we have losses. And I think we calculated the efficiency of that last time of some similar case we had. We calculated the efficiency. And the efficiency we depict or represent by Greek letter eta. And that's just like the N with the longer leg. And that is going to give us a fraction. And if we multiply that by 100, it's going to give us the efficiency in percentage. Alright, so power in, and what's coming out, the power out, loss, and the actual power that we're getting that we can use. And of course the losses are in the represented by arrow coming out of that machine, and usually this would be turned into heat. Here's an example. A DC motor draws with armature 16 amps at 125 volt DC. That's the armature. Now the field winding, we have 1.2 amps at 65 volts, and we are noticing the output of torque of 8.2 Newton meters at the speed of 1750 RPM. What do they want us to calculate? Total input power, output power, and efficiency. Well, that should be easy. We just get the electrical power on the armature, voltage times current, boom, got it. Then the power supply to the field winding, voltage times current, add those two, and we're going to get the total input power. So what do we have here? Solution given, voltage on the X, and what's the X? That's the field. And here's also the current of the field. Current in the armature, supplied power, which is to the armature. We have the torque, we have the speed. Armature power, plug in the numbers, we get 2000 watts, 2 kilowatts out of that. And what are our losses? The field power to excite the field. We get multiply the voltage times current, and that is going to give us 78 watts. So we are out of the, well, no. If we add these two, that's the total power that has to go into this machine for the machine to work properly. So the input power is the armature power plus the field power, and we get, well, 2078 watts because we add these two. Now the output power, remember the formula that I want you to learn by heart? Torque times speed divided by 9.55. Right? Power mechanical. Microsoft, fix it, please. It's going on for years. People pay money for it. There you go. I said my piece. Mechanical power, torque times speed divided by 9.55. Let's see if we can make it to the end of the line without... Oh, there we go. Wow. Alright. Learn that formula. So now we get output power, and what we get, it's also coming out in watts. So the output power with the torque that we measure and the rotations per minute, we got 1503. We're putting in 2078 watts, and we're getting out of it the power that we're actually using. We're getting 1503 watts. So then, of course, plug in the numbers. The 1503 divided by 2078, and we get 72%. Skip a step here. We get a fraction. 0.723, and then multiplied by 100, you're going to have the... I don't need to explain that. If I do, just let me know. Alright, speed of rotation. Speed of rotation. Armature speed by constant, the motor constant, and the field per pole. How to control the speed? Control the field, the magnetic flux in the field by lowering down or upping the voltage in the field. How do we do that? By the PWM idea. Power flow in the DC motor, and pretty much in most of the motors you're going to have that. The input power equals to the, well, not all of them, because some of them, like squirrel cage motor, we are not exciting any field there, but we haven't got to that squirrel cage motor yet. So the armature and the field. So the power, which is the voltage across the armature, and the current, multiply that, and the voltage across the field, multiplied by the current that goes through the field, you get the power, armature, power, field, and you got the total power that you're going to get that you have to put in. The output power, we have the well, we lost the formula here, but do we remember that? Again, torque, make it here, we can do it like this, equals torque times speed over 9.55. Okay, that's the output power, and it's a mechanical power that we have. And of course the efficiency we just calculated. Oh, well, that was a short presentation here. So read chapters 5.3 to 6, 5.3, 5.6 to get this. And then Mr. Liu designed a little type of assignment here, which would be for your own good. Just do it. A DC motor draws 15 amps the source, so we have the amps, 15 amps on the 126 volts at the armature, and we have 1 amp and 70 volts in the field winding. It outputs, so we have the same thing. Calculate the total input power, output power. So we do the same thing that we have done just 2 slides ago, and you're going to come up with a different number. So just practice that kind of stuff. And all right, so you are going to be able to make it to your 5 o'clock class here. And that's it for today's Wednesday's class. And I'll see you tomorrow during the lab. Make sure you have your labs printed. And is there any lab prep? I think there is. There's going to be some calculations there, so make sure you do that. Thank you, and see you tomorrow.